Hey ladies and gentlemen, thanks for getting over here to science. This is a little review session for the final test as well as the interview. Just letting people know that I'm going to do my best to go through these questions, these topics, these concepts, and see if you can't make sense of the information being presented. So one of the first questions you're going to be asked here is to go through and identify the different types of rocks. Now this could be partly related to the rock cycle and so forth, but we'll start off with just a labeling of rock types and kind of move from there. So first off, sedimentary rocks. There's two main characteristics you're looking for sedimentary rocks. You're looking for either fine layers, and when I say layers, I'm talking nice, straight, flat layers. We've got that going on right there, and that's going to be your sediments that are placed down in those layers. No interruptions or manipulations of those layers. Another item that you'll find there potentially is fossils. Fossils are only found in sedimentary rock. All the other two rock types are going to end up beating up the fossils, and the fossils won't survive. And so sedimentary rock is the only rock type that could potentially have fossils. Now, if I take that sedimentary rock and I put it under some heat and pressure, I can take these nice straight lines and get my lines to look a little bit wavy, like we have over here. And again, what we've done is we've taken this rock and we've smushed it under heat and pressure, just like a bunch of layers of, maybe layers of clay or Play-Doh, and we're squishing and smushing and smearing. And you get these layers for sure, but they're foliated. And foliated layers means the layers that are pressed together, but also smeared and smushed and moved around like that. And so that's going to be our metamorphic rocks. Now, if I take either the sedimentary rock or the metamorphic rock, and I just go and turn up the heat and I melt them, or I put them under so much pressure that I literally melt them, I'm basically going to start the rock over again. It's going to be melted, it's going to turn into magma, and that magma, once it starts cooling, is going to yield me two types of rocks, both of them being igneous. So we have igneous and igneous here, but we have rocks with small crystals and rocks with large crystals. Now the large crystals, like this guy right here and all these little black chunks right there, you can see them individually, but this takes a long time. So this would be a slow cool. However, over here, basalt, imagine magma coming to the surface, lava coming to the surface, and finding the first thing they encounter is not air, but instead encounters seawater or ocean water. It's going to cool really quick. And so cooling quick yields small crystals. Crystals you really can't see individually and separated like you can over on this side. And so basalt is a fast cool. Alright, that takes care of this first picture. Let's look at the next one here. Alright, so we're moving into plate boundaries, and we should probably just continue with the first one. We were talking about igneous rock. And so igneous rock is a rock type that is brought to the Earth's surface in the form of magma or lava rising to the Earth's surface. Please don't forget, the main force behind all this continental movements is convection. And that's convection from the Earth's inner cores, moving up through the mantle and reaching the Earth's crust. So, at this point, we've got a boundary running right down the middle of the Atlantic Ocean. A beautiful boundary line here. And we can see the direction is in this left, right, east, west direction. And so because these plates are moving apart from each other, we're going to refer to this as a divergent boundary. And being as that it's a divergent boundary, and now the crust is moved away, we definitely need to replace it. So we're going to replace it with new crust. That seems to be like the main things we do run into. You could argue that there's a bit of a mountain range here, but the mountain range is nowhere near tall enough to stick out of the ocean, so it's a pretty small mountain range. But the presence of new crust is a great place to start on a divergent boundary. Let's head to another boundary type. Alright, so we've got the Pacific plate moving in this direction. We've got the Asian plate right here, and this Pacific plate is actually going to go underneath the Asian plate right there. And if it's going to be coming together like this, we're going to refer to this as a convergent boundary. Coming together, converging. And there's a couple things you can find over here. You'll notice here we've got some, let's see, the islands of Japan are over here. They were formed through volcanoes, which makes sense. If you've got crusts coming together, and the continental crust is here, and the oceanic crust is here, and it's more dense, the oceanic crust will go underneath, and as it goes underneath, the deepest portions of that crust is going to melt, get nice and hot, and it's going to start coming back up, and it's going to come back up and form the volcanoes. So think about all these island chains right over here, all formed by volcanoes. Also, there's this little word right there, and that word is trench. As these plates move under the other plate, they end up bringing the non-subducting plate along with them, and they kind of drag and bring it along. You get this nice deep trench area right here. And so make sure you include trenches here. It is possible to experience earthquakes in this location. It is also possible to argue that there is some mountains, although most of the mountains do resemble and or come from the volcanoes. So, anyhow, this is a convergent plate boundary. Next up, again, plates coming together. We have the Indian plate and the Asian plate. Again, this will be a convergent, but because it's two continental plates coming together, there's really only two things we run into here, and that is mountain building. For those who've noticed, this is the country of Nepal, which means there's a certain mountain range right here, referred to the Himalayas, Mount Everest, part of that, and so forth. But also, you can experience some earthquakes in this area, and we know that Kathmandu, about 2 years ago, had a pretty intense earthquake that kind of beat the place up, but again, it's on a fault line. So, all right, final boundary type. We have the San Andreas Fault right here, so this is California, okay? And we have the, this would be the North American plate, and this is it the Pacific plate or is it the Nazca plate? It might actually, I can't actually remember which plate it is. But this plate is moving north, this plate is moving south, and so the big thing here is this is going to be called a transform boundary. The plates are trying to slide past one another, and in doing so, they do get hung up on each other, and when there's a sudden release of energy, booyah, earthquakes big time. So, there you go. There's your main boundary types. Don't forget, all powered by convection, touch of gravity, but mostly a convection current form power. All right, so this is a question about whether it's weathering and erosion. We got a tree here who's breaking, cracking, beating up the sidewalk, and while sidewalk you could argue is being a rock or not, in geology we call it industrial conglomerate. It's me fancy way of saying sidewalk. But we got a picture right below that also is showing roots growing into a rock. But so if we're breaking rock, that's going to be weathering, all right? And if we're over here, we're talking about the Mississippi River and all the sediment it carries and displaces down here in this triangle shape referred to as a delta. Notice the shape is that of a triangle, Greek for delta. This is going to be erosion. This is where the material has been deposited and it's been transported and it no longer is in the same place it was before. So that's erosion. Next, ooh, cool. We're at this time of year, folks. Not only is it maple syrup tapping season, which is awesome, it's also a time to go and discuss potholes. And so potholes, we got to crack this pavement up, and so you just get a couple little cracks, and the cracks be the weathering. You slap some water in there, you know that water will expand when it freezes, so we get something called ice wedging, where all of a sudden the ice is pushing the rocks apart. And then maybe between plows coming along, cars coming along and kicking the rocks out of the way, we now have movement of the rock. That's going to be erosion. So weathering here for the cracks, erosion is the movement. Excellent. Nice. All right. So along those lines of dealing with plate boundaries and plate movements, we can start addressing the evidence that scientists use for presenting the idea of continental drift. And so we got 6 examples right here, and I'll just start off right off the bat with fossils. This picture right here that shows some ancient organisms that no longer exist, so they're extinct, but these organisms did live in these boundaries that are shown here, and most of these animals that are being described in this picture are land animals. They are not the ocean-faring, swim 3,000-mile kind of creature. And so for them to exist on the east coast of South America and the west coast of Africa. The only way for this to have been true is for these continents to be together at some point in past. You are correct, this is Pangea. And so fossils, check. Next up, let's get over to that Pangea idea. Here we go, a nice little picture of Pangea, all the continents together, and we've got these boundaries and these borders that are very similar to not only the edges of the continents, but also the mid-Atlantic spreading center that we talked about earlier. That's going to be continental edges. Another technique that's used for discussing and describing this movement, which it's not exactly a law, which is really too bad because the data is just beyond conclusive here. But scientists have been using lasers and satellites, GPS and so forth, to go and monitor the actual movement of the continents. And so there is C down over here on this. Next up, paleomagnetism and spreading centers. Beautiful. So this is old, this is newer, and as we go through time, the plates do spread apart, and so there's your spreading centers. But also, as they spread apart and new magma comes to the surface here, and we get new crust forming, the crust will actually go and preserve the magnetic field of the Earth at the time. And so the colored forms here of orange and red and so forth are all normal magnetic fields, but the white is referred to as reversed magnetic fields. And so that's going to be paleomagnetism. All right, next up, glacial deposits. Well, we're running out of pictures here, but we're going to go right off with the one that happens to have a bunch of white material here. That's snow and ice and glaciers. And notice it also says South Pole. And so as the snow and the ice moves out in this direction, it brings rock and deposits with it. And this blue line on the outside here is actually a line of till sediments that can be found in all these continents, which clearly are not together anymore. And so glacial deposits is E. Which leaves us with the last one here. These are the same two pictures. You will know right here that it talks about things like sandstone, basalt, glacial tills, and so on and so forth. These are rock layers, these are rock types, and so we are now referring to this picture as F, rock layer similarities. Cool, we're almost done here. Topography map. We have some tall peaks. When you start seeing all these circles coming together, that's going to be one of your tall peaks. So there's A. We also have another tall peak over here, which means in between we'd have a valley. So there's a low point between. We have a river right here. River is shown by these little V's that form. Another river right there. Another river right there. And lastly, a river over here. And so those are E, E, and E, which leaves us with the steep and the gentle slope. Now, steep slope. Anytime you see lines together really close like that, steep slope, steep slope. Gentle slopes, where the lines are spread out, like right here, that's a gentle slope. That's a nice open meadow up in the mountains right there. So that would be a gentle slope. And this is a topography map. Cool beans. Last picture. Ahaha. Last but not least, we are talking about fossils. So the oldest fossils, law of superposition states, oldest fossils are going to be found at the bottom layers, and therefore the youngest will be at the top. And just simply trilobites are the oldest, and in this case here the fern is the youngest, and that takes care of our little interview right here, folks. I hope you study, I hope you prepare for the final test, and make sure you get this interview done before the final test. Alright, you have a great night. Talk to you soon.